Alright, in this video we're going to go over how to do the calculations for the molar mass of butane lab. And I'm going to give you some instruction on how to do that with some fake data that I collected in the lab. So your numbers will be different, but you can follow this procedure for doing your calculations. Alright, for the lab report, the part A is finding the partial pressure of butane. Now, at the beginning of chapter 11, we learned that Dalton's law of partial pressures tells us that the total pressure of a gas mixture equals the partial pressures of each in the individual gases. So if you had a mixture of gases A and B in a container, if you add up the partial pressure of A and the partial pressure of B, you would get the total pressure. This makes sense. Now, an application of Dalton's law of partial pressures is when we collect gas through water displacement like we did in this lab. In that case, the total pressure is the atmospheric pressure, and the two gases that were collected in our graduated cylinder were butane and water vapor. So we have water vapor pressure. So if this was our graduated cylinder inverted in the water, okay, it's submerged in water, what was collected in here was a mixture of both butane gas from the lighter as well as water vapor that escaped into the gas phase from the surface of the water here. So it's a mixture of those two gases. Now you held your graduated cylinder, once you were done filling it with gas, you held it so that the water level inside the graduated cylinder matched the water level outside of the graduated cylinder. And you did that so that you would know that the external pressure on the water in the beaker here equals the internal pressure of the gas on the water. And so the external pressure is the atmospheric pressure. So the atmospheric pressure is equal to the pressure inside the container. The atmospheric pressure on the outside is equal to the partial pressure of butane and the partial pressure of water. Alright, so you measured the atmospheric pressure using a barometer in the classroom, and say you may have measured it in inches of mercury, and if you did, you can use the conversion factor on the lab sheet to make the conversion to millimeters of mercury. If you found it in inches, then you can go to millimeters using the conversion factor on the paper, but many of us recorded the partial pressure in centimeters of mercury. So say you got 75.60 centimeters of mercury. Remember, you always want one uncertain digit in your measurements, and since there were markings for the tenths of a centimeter, I read to the hundreds. So I need to convert the centimeters of mercury, and that was the atmospheric pressure, to millimeters of mercury. So I put centimeters down here and millimeters here, and I know that there is 10 millimeters in 1 centimeter. So I end up with an atmospheric pressure of 756.0 millimeters of mercury. Now we know that millimeters of mercury and torr are the same thing. Okay, so either one of those, it's 756.0. Now, so that's this number right here. So P atmosphere is 756.0. We'll just go ahead and say it's torr, because the other number that we're going to fill in, we're trying to find the partial pressure of butane in this step. The other number that we know is this vapor pressure of water. The vapor pressure of water, as we studied in chapter 11, is dependent on the temperature of the water. Well, the temperature that I took, which is going to be different than what you took, let's just pretend I was here in the summer, and it was 30.2 degrees Celsius. That's a good bit higher than what you should have gotten. But say that was my temperature. When I add 273 to that, I get, well, I don't need to do that yet, actually. All I need to do is take this temperature and look at what the partial pressure would be at 30.2 degrees Celsius. And that is roughly 31.82 torr. So you just kind of go with the partial pressure with the temperature that's closest to the one that you have. So according to our chart there on that table on your handout, it's 31. The partial pressure of water at 30.2 degrees Celsius is about 31.82 torr. Okay, so I don't have to change that to Kelvin yet, but I will later. All right, so I have torr minus torr, my units match, so I can subtract, and when I do, I get the partial pressure of butane, so I take 756.0 and subtract 31.82. The partial pressure of butane is 724.18 torr. Now, if that was my final answer, then I would round this to having just one decimal place, 724.2. But I'm using this partial pressure of butane in part B, and then using part B and part C. And so I'm not going to round my answers until I get the final answer, which is my molar mass of butane in part C. So I'm going to leave the partial pressure of butane at 724.18 torr. All right, let's go on to the next step. So the next thing that we're going to do is find the moles of butane gas. Well, we know that the gas law that lets us calculate moles of gas is the ideal gas law, and so that's PV equals nRT. And I want moles of butane gas. So I need the temperature of the butane gas, I need the volume of the butane gas, and I need the pressure of the butane gas. Okay, so here I'm going to use, I just calculated this right here, the pressure of the butane gas in part A. So that is 724.18 torr is what I had calculated in part A. Now, I have to convert that to atmospheres in order to use this equation. So I'm going to divide 724.18 torr divided by 760. That will actually convert it into atmospheres. Okay, so now I have a pressure in atmospheres. The volume of the butane gas, you collected 100 milliliters of gas, and your volume, because there were markings for every milliliter, should read to the tens place. So you had 100 milliliters of butane gas collected. Now technically there's also water vapor in there, so it would be slightly less, but we're still just going to say there was 100 milliliters of gas, of butane gas. So volume must be in liters when you use PV equals nRT. So when I convert 100 milliliters into liters, there's 1,000 milliliters in 1 liter. I get 0.1000, all those significant digits because I had so many over here. So my volume is 1.1000 liters. Okay. Let's see, this is going to be in atmospheres. Okay, PV equals N. N is what I'm solving for. I'm trying to find the moles of butane gas. The R is the gas constant, 0.0821, and that's liters times atmospheres over moles times Kelvin. Okay, that's R. And then T, now my T has to be in Kelvin. I measured it in Celsius. Mine was 30.2 degrees Celsius. And now I'm going to add the 273 to that to figure out the temperature in Kelvin. If it was my final answer, I would round it so it just had 0 decimal places, but remember we're not rounding until we get to the final answer. So when I add those two together, I get 303.2 Kelvin, and that's the temperature I'm going to put here, 303.2 Kelvin. Okay, so the kelvins are going to cancel, and the moles, this is moles over here, the moles are going to cancel, the atmospheres are going to cancel when they're divided, and the liters are going to cancel when they're divided, okay? So all the units match, PV equals nRT. Now I need to solve for N, and when I do that, the N that I get, I don't want to round this number yet, we don't round until the very end. This is all the numbers I had in my calculator, 3.827899969, and you can, yeah, times 10 to the negative third moles. Now that's how many moles of gas, butane gas, that I had, moles of butane. Okay, and like I said, if this was my final answer, I would round this to an appropriate number of significant digits, but this is not my final answer. I'm just walking you through the steps. My final answer is the molar mass of butane. So let's go and find that. So for part C, finding the molar mass of butane, well, molar mass, we know, is grams over moles. Okay, the units are grams per mole because you take the grams and you divide it by the moles. Well, my initial mass of my lighter for my first trial was 9.68, and then my final mass of my butane lighter was 9.26. Now when I subtract those two, I get 0.42 grams. So that's the mass of butane that was released into the graduated cylinder. To find the molar mass, I then would divide that by the moles, which I just found in part B. So this right here comes from part B, and I just calculated this using the initial and final mass of my lighter for the first trial. So the molar mass is going to equal 0.42 divided by my moles, which was this long, for the last slide, 3.827899969 times 10 to the negative third moles. Okay, so when I divided that, I got 109.7207355. Okay. The molar mass is my final answer. Now I'm going to evaluate in part D the accuracy of my final answer, but this is my final answer, so I'm ready to round. I'm ready to round this molar mass to the appropriate number of significant digits. Well, if you look back through how many significant digits are in each of your measurement, you're going to find that the change in mass here has the least number of significant digits. This has 2 significant digits, and there's no other measurement that has less than 2 significant digits if you've done your significant digits correctly. So I'm going to round my molar mass to 110 grams per mole. Okay, and that's my final answer for part C. All right, for part D then, for the calculations, percent error. Now calculating percent error, the equation is percent error equals your measured value, so what you actually got in the lab, that was my 110 grams, minus the accepted value, which we'll talk about that in just a second. Measured minus accepted all over the accepted value times 100. So in lab, I measured with my data, I got a molar mass of 109.7207355. Now, I put the unrounded molar mass here because I want to get the most accurate picture of my percent error. So I don't want to use a rounded number here. So the 109.7207355, which I got from part C before I rounded. And then I want to subtract the accepted molar mass. This was my calculated molar mass, the one I found in the lab with my data of butane. Now I want the theoretical or the accepted value. Well, butane has a chemical formula of C4H10. And when you find the mass of 10 hydrogens and 4 carbons, each carbon is 12.01 grams, and each hydrogen is 1.01 grams. When you multiply 12.01 times 4 and 1.01 times 10 and add those two together, you get a molar mass of 58.14 grams per mole. So I should have gotten 58.14. Now I didn't. So the question is, how far off is my data? Well, I'm going to plug in. That's what percent error tells me. So I plug in my 58.14 here. That's the accepted value, and this is the accepted value here, times 100. And then when I evaluate that, I get 89%. So I was almost double, which you see there, almost 100% more, almost double what I should have been. And that's okay. Now, why did I round that to 2 significant digits? Well, remember, really, this number right here had been rounded to 2 significant digits. And so my least precise measurement, which was the change of mass, had just 2 significant digits. So that's why I picked 2 significant digits for my percent error. So what you're going to do is do those calculations for all 3 of your trials, showing all of your work for each of the 3 trials. And then once you have your percent error for the 3, you can decide which of the 3 trials is your best trial. That would be, of course, the one with the lowest percent error. So hopefully I would have another trial where my percent error was much lower, and that would be the one that I'm going to put in the lab report. Okay, so you'll do all 3 trials, and then the one that goes in the lab report that you're going to type up is the one with your lowest percent error.